Pretty easy. All right, so first things first, we have to learn how to recognize an acid and how to recognize a base. Turn the light on here. Can you guys see that well enough? Okay, it's recording. All right. So you got this worksheet, right? And on the top is essentially the rules that you have to follow. So when we finish chapter 15, which is an introduction to equilibrium, we're then going to go on to chapters 16 and 17, which are entirely focused around equilibria that deal with studying acids and bases. So it's kind of critical for us to learn how to name these things and how to write formulas based on those names. So let's start with acids. If we look at this worksheet, the way that we recognize acids is that they all start with hydrogen. All right? So those chemical formulas are all going to start with hydrogen. For the most part. There are a couple of exceptions to that. All right? So if you look here at all these examples, they start hydrogen, 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 hydrogen. The ones that I'm skipping over, like 22 and 27 on the right-hand side, 31, that's on the right-hand column. Let's see on the left-hand column. What am I going to skip over? 3, 8. Well, 11 is kind of an iffy one. 12 I'm going to skip over. Those other ones that I've circled here on the sheet are considered bases. What do they all have in common? They end in OH. All right, so acids start with hydrogen, bases end in OH. Okay? All right, so bases are easy enough to name because all you do is you name the metal and then you tack the word hydroxide on the end. These are metal hydroxides. About the only funny thing that you might have to do is that if the metal is one of these transition metals, you might have to add a Roman numeral. But those are really easy to name. So for instance, if we go over here to number 3, we have this formula, CaOH2. What's that called? Well, I look at the first element, it's calcium. Is calcium a group A or a group B metal? Do you guys remember the difference between A and B? A is non-transition, B is transition. Is calcium a transition metal? No, so I don't need a Roman numeral. So what do I call this? Calcium hydroxide. What about number 8? NaOH. Oh, you can't see that. NaOH. That's sodium hydroxide. What about AlOH3, number 12? Aluminum hydroxide. Okay, you get the gist? Well, number 11 is a special case. It's not a base. All right? So those are, bases are easy enough to name. So I'm going to give you a minute. I want you to go ahead and name number 22 and 27. Beta, what'd you call number 22? Lithium hydroxide. Good. Roxy, how about 27? Potassium hydroxide. It's a special one. I'll get to them in a little bit. Okay? Those are actually organic acids and bases. And you name them a little differently. So we're going to hold off on doing those for the time being. Okay? All right. So you see the rest of this worksheet is acids. How do we name those? Well, first things first, if we go back to the rules up top, we need to look and see whether the acid is binary or it's ternary. So what do I mean by binary? Two elements in them. One of them is going to be hydrogen. All right, so where do you see an example of a binary acid? So the first one that I see on the left-hand column would be number 5, and then number 10, and then 13. Okay? When you name those are the only ones that you're allowed to use the hydro prefix. Okay? So the way that you name these is you take hydro, you tack on the root of the second element, and then you tack onto that ic acid. So if you look here, what is this anion called? That's chloride for number 5, right, for HCl. All right, so this would be hydrochloric acid. All right, what about number 10? What would we call number 10? Good guess, iodic acid. It's a little weird to have an O-I-O combination in the middle of that word, but that is how you write it. And then how about number 13? What would you call that? Hydrofluoric acid. All right, so let's take a look at the second column. Are there any binaries over here in the second column? Number 21, 24, 25, 30. Why don't you take a minute and name those by yourselves? There is none. You still name them the same way? Yes. We were just talking about that. I love you. Just remember that. Well, we're getting there. Hold on. Let's do 21 first. All right. So who's got 21? What do you have for 21? Yeah, Michael? Okay, 21 is hydrobromic acid. Good. And then 24, we did already, right? It was the same as number 10. It's hydroiodic acid. All right, 25. This would be hydrosulfuric acid. Not hydrosulfic, hydrosulfuric. All right. And then number 30. What's that, Roxy? Hydrophosphoric. Good. All right. Okay, so again, I can't stress enough. The only time that you use that hydro prefix is for binary acids. For every other kind of acid, you can't use hydro anymore. 34. Oh, yep. You're right. What'd you call that? Hydrochromic. Good. All right. Let's go back to the rules. Now let's talk about the ternary acids. So to name the ternary acids, you have to look at the polyatomic ion that is attached to the hydrogen and recall what that polyatomic ion is called. So for instance, let's take a look at number 1 for instance. You see that polyatomic right there, ClO4? What is that called? ClO3 is chlorate, so ClO4 is perchlorate. So this sucker here is called perchlorate. The name for the acid is dependent on whatever ending you have on that polyatomic. So if it's a polyatomic that ends in 8, then we would call this perchloric acid. You replace the 8 with ic acid. If the ending of the polyatomic is ite, then you replace it with us acid, OUS acid. All right, so for instance, number 1, this was called perchlorate, so this is going to be called perchloric acid. Take a look here at number 18. You see SO3. What's SO3 called? No, that's not sulfate. Sulfate is SO4, right? SO3 is sulfite. So what would you call this acid? You replace the ite with OUS acid. So this would be called sulfurous acid. Okay? All right, let's do a couple more together. Let's take a look at number 2. HCOOH. Yeah, no, this is an acid. It's an organic one. Let's skip this for today. Look at number 4. H3PO4. What do you call PO4? What's the name for that polyatomic? Phosphate. So what would this be? This acid would be phosphoric acid. No. Hydro is only for binaries. Okay? All right, take a look at H3BO3. What is BO3? It's called borate. So this would be boric acid. How about number 7, H2SO4? What's SO4 called? Sulfate. So what would I call this? Sulfurous. No. Oh, bad girl. This is sulfuric acid. Nothing weird. Nothing weird about it. Okay. HNO2. What's NO2 called? Nitrite. So then this would be called nitrous acid. Let's skip 11. Let's come down here to 14. H3PO3. What's PO3 called? Phosphite. So this would be what kind of acid? Phosphorus acid. How about, ooh, this is a toughie. Cyanide. But it's not binary. It's not binary. What do I call it? Yeah, no, by name. Why don't you look it up?
There is no signal in this class.
There's no signal in this class? Yeah, there is.
No, you don't want to.
Ask Siri. What does Siri say HCN should be called?
Siri, how do you say HCN?
Okay, what if you ask, okay, so there's two possibilities for this name, right? We could either call it cyanic acid or hydrocyanic acid. Why don't you look up those two? Formula for hydrocyanic acid. Big old question mark. Is it cyanic or is it hydrocyanic?
Shut up.
Sure, but if as an acid name, like if you type in type in formula for cyanic acid, see if anything comes up. Thank you. Help her out. Does it come up with anything?
That's what it says.
Fine. The formula is HCN.
HCN.
Do you find that same formula if you call it just cyanic acid? Not cyanic. All right. So listen. Okay. So let's go back to me yelling at Omar a second ago about using the prefix hydro. Okay, so just you got hydrocyanic, not cyanic.
Cyan, like hydrocyanic
Acid. Okay. All right. So for the most part, that hydro prefix is going to be used for binary things, but here's an exception. So really, don't just look to see whether the thing is binary. Look to see whether or not that polyatomic ion ends in "ide." All right? It's really when the name of that ion on the back end, the anion, ends in "ide" that you use that hydroic acid rule. Okay? It's just sometimes it's easier to see whether it's binary or not. But there are, every once in a while, things like HCN that pop up that you would have to use a hydro on, even though it's ternary. All right, let's take a look at number 16. What is ClO3 called? Chlorate, so this would be chloric acid. And then how about CO3, what's that called? Carbonate, so this would be carbonic acid. Okay, for time's sake, let's flip to the back. We're not going to do all this, relax, let's just do a couple. All right, so it says write the formula for each of the acids listed below. All right, so let's start with nitric acid. So if you don't see the prefix hydro, what does that tell you about the element? Or about the compound? There's ternary. So you have to have hydrogen in front. Hydrogen usually has what kind of a charge? 1 positive, right? And if it's called nitric acid, then the anion is nitrate. What's the formula for nitrate? NO3, what's the charge on that? 1 minus. Okay. When I cross the charges to figure out the subscripts, what is the formula for nitric acid? HNO3. All right, number 2, hydrocyanic acid. Okay, erase your mind from 2 seconds ago. Okay. Hydrocyanic means that I have hydrogen and cyanide. What is the formula for cyanide? CN, the charge on it is 1 minus crisscross applesauce. What do you end up with? HCN. Let's go down a little bit. One that ends in us, because I want to try one of these so you can see it. Number 8. Okay. So nitrous acid. Binary or ternary for the most part? Ternary. The first element is going to be hydrogen, has a charge of +1. If it's nitrous acid, it's the compound between hydrogen and nitrite. What's the formula for nitrite? Charge is 1 minus crisscross applesauce. What do you end up with? HNO2. Let's do something a little bit more complex. Go down to 13. Carbonic acid. Binary or ternary? Ternary, so it starts with hydrogen. The other ion in that material is carbonate. What's the formula for carbonate? CO3 2 minus. When you cross the charges to get subscripts, what do you end up with? H2CO3. Get the hang of it? All right. Why don't you take a moment and do as much of column 1 as you can? Don't worry about formic acid. Don't worry about it. Those are organic things. We'll get to that. I would suspect like 10, 12. Is it 15? No, it's an hour. Why is
Started
it?
at 9:12.
It's a 60-minute day.
Yeah,
Yes, it's a Tuesday
that's
on a Wednesday because we have one less hour.
No, we get out at
10:02.
10:15. No, that's
Okay, listen, seriously. Listen, you're wasting your 15 minutes. Get to the college. I think so. Huh? 8 years, but I only recently started learning a lot. To be honest, I don't really know. It is. Yeah, like on days like today when person's not gone and you gotta give them else. It's not easy. It's not easy. That's why we become bitter and jaded after a while. Because we're tired of jumping through the hoops. Hey, Adik! What did you discover about my worksheet, Adik?
What?
You discovered something. I see you constantly flipping it back and forth.
Same exact thing.
Right, they're the same.
You just wrote the answer.
So the front is the answer key to the back and vice versa. So far, you getting them right?
Actually, that's a lie. It's 34, 34.
Listen, it's not perfect. Relax. Nothing in this world is perfect. All right. Are you sort of getting the hang of this? It's easy, right? Okay, all right. Because Cameron just reminded me that we got 10 less minutes than I thought we did. Let's move on to this other sheet that I gave you. Reactions of the week. Yay. These are actually really easy. These are really easy. Okay. We're going to do oxides with water. All right. And so the rules are actually pretty straightforward. We're going to do metal oxides with water, non-metal oxides with water, and metal oxides with non-metal oxides. All right? So the rules are here in the middle. So the way that you recognize these questions is that you're either going to have a binary metal oxide or a binary non-metal oxide with water. If you look at 1986 to 2003, you'll notice, number one, that it's a fairly popular category for them to ask. And in every case, well, most every case, take a look. Solid sodium oxide is added to water. Sulfur trioxide gas is added to water. Solid dinitrogen pentoxide is added to water. Water, 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 water. 99 is an exception. Water, 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 water. So that's going to tip you off that you're going to do what we're going to show you next. Okay? All right. So once that you've identified that this is one of these oxides, you're going to look at the reactant and you're going to determine, well, is this a metal oxide or a non-metal oxide? Okay? All right. So sodium oxide. Does it start with a metal? Is sodium a metal? Yeah. So this is a metal oxide. So the rule here is that metal oxides with water form bases. All right? Metal oxides with water form bases. What do you think non-metal oxides with water form? Acids. And then if you have a question like 1999, where you have a metal oxide, sodium oxide, combining with a non-metal oxide, carbon dioxide, then what you do is you synthesize. You put them together. Okay? All right. The only thing that you have to recall here, the only thing that you have to do that's special here is on the product side. Because water is present, you're making solutions. When it comes to writing acids and bases in net ionic form, we don't think about solubility properties anymore. You break them down into ions depending on whether they're a strong base or a strong acid. You only break those things down. If the product that you're going to make is going to be a weak acid or base, you leave it together. All right? So what are strong acids? What are strong bases? So you're going to have to remember that the strong bases are hydroxides with any of the alkali metals. So a group 1 hydroxide or a heavy group 2. So for instance, the calcium hydroxide, strontium hydroxide, barium hydroxide. So what I mean by heavy group 2 is, so remember this is group 1 right here, first column. By group 2, heavy group 2, I mean the heavier members of that family. All right? So if you produce one of those bases, they're strong, on the right-hand side, you split them into ions. All right? In terms of acids, you do the same thing. You only break them apart if they're strong. And you're going to have to memorize this. So the strong acids are acids with any of the halogens, with the exception of HF, right? So HCl, HBr, HI, nitric acid, sulfuric acid, and yeah, that's about it. So if those are the products that you make, you split them apart. All right? If you don't make those products, you keep them together. All right? So let's take a look at question from 1986, the first one. It says solid sodium oxide. So let's start by writing the reactants. How do I write that? Na2O is added to water. Right? So those are the reactants. So I've got a metal oxide with water. What am I supposed to make? A base. The base is essentially going to be that metal tacked on with hydroxide. So sodium hydroxide. All right? Is sodium hydroxide a strong base? Yes. So what do we do on the right-hand side? Keep it together or break it apart? Break it apart. So what you write on the right-hand side is Na plus OH minus. And then you would go back and balance it to make sure that you have 2 oxygens, 2 hydrogens on both sides of the equation. All right? Let's take a look at the next one, 1988. Sulfur trioxide gas is added to excess water. All right? Sulfur trioxide, what's that formula? SO3. I'm adding it to water. Is that a metal oxide or a non-metal oxide? Is sulfur a metal or non-metal? Non-metal. So what am I supposed to make? An acid, okay? The simplest way to come up with that formula for the acid is just to shove all the letters together, put hydrogen first. All right? So let's do that. H2SO, what subscript would I use to make sure that was balanced? 4. Oh, goodness gracious, H2SO4. Is that a strong acid or a weak one? Strong. So should I leave it like that? No, I should rewrite it. How should I rewrite it? H plus SO4 2 minus. All right, so you break it apart into the ions that make it up. You have hydrogen ions and sulfate ions. All right, let's take a look at 1990. Solid dinitrogen pentoxide. All right, so what's dinitrogen pentoxide? N2O5 with water. Is that a metal oxide or a non-metal oxide? Non? Okay, so let's see if you can predict what happens when you shove all the letters together. What should you get? Huh? Because I have 3 oxygens there and then a 4th one there. It balances out my atoms. Okay? All right. Ooh, what do I get here if I just shove all those letters together and put hydrogen first? It's always hydrogen first, oxygen last, by the way. H2, keep going, N2O6. What do you know about these kinds of compounds? You can certainly reduce those subscripts. And if you reduce those subscripts, what do you end up with? HNO3. Oh, is that a strong acid or a weak acid? Strong. So what should you do with it on the right-hand side? Break it apart into H plus and NO3 1 minus. All right, next, 1992. Solid potassium oxide is added to water. All right, so what's the formula for potassium oxide? K2O. I'm adding water to it. Metal oxide or non-metal oxide? Metal oxide. Do metal oxides and water make an acid or a base? Base. So the base is going to be between the metal and hydroxide, right? So potassium hydroxide? Is potassium hydroxide strong or weak? It's strong. So on the right-hand side, what do I write? K plus plus OH minus. And guys, I hope you realize I'm not really paying too much attention to the balancing right now. I just want you to focus on writing the formulas. But we would eventually have to balance these suckers out to make sure the number of atoms is the same on both sides. All right, next one. Phosphorus 5 oxide powder is sprinkled over distilled water. So what's the formula for phosphorus 5 oxide? P2O5, correct? I'm adding it to water. Metal oxide or non-metal oxide? Non-metal oxide. So do I make an acid or a base? If I'm making an acid, I just shove all the letters together, hydrogen first, oxygen last. What would you end up with? H2P2O6. And again, what could we do with those subscripts? Reduce them. If I reduce that, what do I end up with? Ooh, that doesn't make sense, does it? What's the charge typically for phosphite? This one kind of stinks. You can't have that, because the charge for phosphite typically is 3 minus, and the charge for hydrogen is 1 plus. If you were to cross those subscripts, you wouldn't end up with H1PO3. So adjust it. Maybe it's H3PO3. Okay? Is that a strong acid or a weak acid? Weak, leave it together. Okay? You get the hang of these? If you can get it to balance, you can do that. Because what you're trying to do, listen, I'm going to be very honest with you, Rachel. Some of these, I can look at them, and from experience, I know what the products are, just because it's rote memorization. But some of them, it's a shot in the dark. I'm taking a guess. So I have to take the best, most educated guess. All right, so you work your way down, right? So, like for instance, if you reduce it, you realize HPO3. Well, that's an impossible formula based on the charges for these things. then you go back and you think to yourself, okay, well, PO3 I know is a polyatomic ion that could definitely come out of this. Let's figure out what the subscripts would be, knowing that this is 3 minus and 1 plus. You got to give them the most reasonable answer, and it's okay to make an educated guess. Science is all about making educated guesses. No one was there the day the Big Bang happened. It's all an educated guess, right? Darwin didn't really see those boobies on the Galapagos evolve in front of him, right? They're birds. They're birds, okay? He didn't physically watch them evolve. It's an educated guess. They were boobies too on the Galapagos Island. All right. Okay. I did. Okay. That's because, Lexi started the whole period off with... Okay, all right. Anyways, let's take a look at 1999.
Are you still recording this?
Yeah, I'm still recording this. Okay. Relax. Okay, carbon dioxide gas. I did. Carbon dioxide gas is passed over hot, solid sodium oxide. All right, so this is the one in all these years where they didn't have water in it, but we got 2 oxides. Okay, we have carbon dioxide and sodium oxide. So the formula for sodium oxide is Na2O. All right, so when you have a metal oxide with a non-metal oxide, you're going to do the same thing that we were doing when we were coming up with the formulas for the acids, shoving the stuff together. You shove all these letters together, metal first, oxygen last. All right? So what would you end up with here if you took sodium oxide and carbon dioxide? Would we end up with sodium carbonate? Is sodium 1 plus and carbonate 2 minus? What would the subscripts be if you did that? Would it be that? Look, you see this formula right here? All I did is I just shoved all the letters together. I put sodium first, oxygen last, and I added up the oxygens. I clustered them together. Are these really the subscripts that you would have if you took those ions and crossed them? Yeah, so we're done. It's balanced. Do I split it up? No, because there's no water here. Okay? So,
That's not an acid.
no, because it doesn't start with hydrogen.
It's not a base.
Nope. Yep. It is a troll question. He's right, because it's an oxides question. All right? It is a total troll question. All right, so listen, we got 2 minutes left. Let's quit. I want to stop recording. All right. All right, guys, so your homework, you need to do reading notes for 15.4 to 15.6. And then what else does that say up there?
First period, see lecture.
Oh, first period needs to watch the lecture on Blackboard. And I can't turn this off. Why won't it stop?
That's all.